Okay, so today we're moving on to 6.4, looking at exponential growth and decay. So exponential growth and exponential decay are two types of exponential equations that we'll be looking at. So exponential growth is going to be when the quantity is increasing by the same factor. So in other words, it's a multiplication pattern by a number bigger than 1. An exponential growth function is going to be represented by this equation. So A actually represents your initial amount, and R represents your growth rate as a percent changed to a decimal, and T represents time in years. So exponential decay is going to be when a quantity decreases by the same factor. So that's when you're multiplying by a decimal or fraction, so a number between 0 and 1. The exponential decay function is going to be very similar. The only difference is, notice on growth, it was 1 plus r in the parentheses, and on decay, it's 1 minus r. So you're subtracting your rate from 1 instead of adding it to 1 because numbers are getting smaller over time. And then we're going to look at compound interest. So compound interest is something like if you have money in a savings account at the bank, you're earning interest on it. So this next section, exponential growth function, exponential decay functions, that's a repeat. We just copied that down up above. You don't need to copy that again. But the compound interest, you do want to add on this to that definition you just wrote down. Okay, so this tells you what each of your variables are. So P is your principal. Principal is another word for your initial amount. R still stands for your interest rate. In this time is going to be the number of times your interest is compounded per year. So if it's monthly, that would be 12. If it was quarterly, that would be 4 times a year, and so forth. So you'll divide your rate by how many times a year it is compounded. And then that exponent is an NT. It's kind of hard to see on here. The exponent is an NT. So your exponent is still time, but you also multiply that time by the same N by how many times per year it's compounded per year. So we'll look at how to use that equation today too. Okay, so let's take a look. In 2005, there were 100 rabbits in Polygon Park. Population increased by 11% each year. Write an exponential growth function that represents the population T years after 2005. So we are going to be using this equation here. So the first thing we need is A, our initial amount. So it's going to be y is equal to our initial amount, which is 100. And then in parentheses, we're going to put 1 plus, and then our equation says that the next thing we're going to have is R, which is our rate. So it says it's 11%. 11% is the same thing as 0.11 or 0.11. So that's going to be what goes in our parenthesis. And it says after T years. So T is our exponent. Part B then, it says, what will the population be in 2025? So T is how many years after 2005? So 2025 is going to be when our T is 20. Okay, and then it says round your answer to the nearest whole number. This is we're talking about bunny rabbits. You can't have a part of a bunny rabbit. Either the bunny's alive or it isn't, even if it's missing a limb, which is kind of weird to think about, but even then it's still a bunny. So when you plug this into your calculator, make sure you're simplifying what's in your parentheses first, then take that to your exponent of 20, and lastly multiply by 100. And when you do that, you get 106 rabbits. If you can't get 106, if you're getting a different number, make sure tomorrow in class you ask me to show you how to do it on your calculator that you're using so that you know how to put it in correctly, so you are following that order of operations. Okay, the next section, determine whether the table represents exponential growth or exponential decay or neither. So growth would be when you have a multiplication pattern and the numbers are getting bigger. Decay is going to be when you have a multiplication pattern and the numbers are getting smaller. And neither is going to be when it's not a multiplication pattern. Okay, so on the first one, to go from 20 to 30 to 45 to 67.5, we're actually multiplying by 1.5, which means this is going to be an exponential growth function. On the next one, 160 to 40 to 10 to 2.5, I'm actually dividing by 4, which is the same thing as multiplying by 1/4. So this is a decay, exponential decay. The next one, I'm subtracting 10. Subtraction is actually linear, so it didn't ask us whether it was linear or not, so this one would actually be neither. But if you want to be more specific, it is linear. And the last one, this should be a -1. I'm not sure why they showed up on different lines. If you go from 4 to 10 to 25 to 62.5, we're multiplying by 2.5, so that would be another exponential growth. All right, the next section, determine whether each function represents exponential growth or exponential decay. So first of all, you're looking at the number in your parentheses to determine this. If the number in your parentheses is bigger than 1, then you know it's going to be growth. If it's smaller than 1, you know it's going to be decay. So check each of these, see if you can determine what they are. So number 6 would be decay. Number 7 would be growth. And number 8 would be decay. So that's the more straightforward part. Then it says to identify the percent rate of change. In other words, we want to know what R is. So I'm going to start with number 7, the growth one. It's a little bit easier. So remember our formula in the parentheses is 1 plus R. So 1 plus what will give me 1.08? Well, it would be the 0.08. So 0.08 is the growth rate, but we want it as a percent. So 8 as a percent, move the decimal over 2 places, would be 8% growth. So now let's look at the decay ones. The decay ones, remember our formula is 1 minus some number. 1 minus what number will give me 0.95? Well, if I set that up as an equation, I can actually solve it, and I get that R is 0.05. So the growth is a little bit more straightforward to see. The decay, you actually have to think about what number would I add to this to get to 1. That's the rate, and then change that number into a percent. So that one would be 5%. So you have to be careful in the decay. You can't just take the number in the parentheses and move the decimal over. It's that number plus what will give you 1, and that number is what you're changing into your percent. So 3/4 is the same thing as 0.75. So when I'm thinking of 1 minus what number would give me 0.75, well, that would be 0.25. And then when I change that into a percent, that's 25%. Okay. Last section is our compound interest. So compound interest is a specific type of growth rate, exponential growth. So let's take a look at it. So let's remind ourselves what our formula is. Our formula is y is equal to p, and then in parentheses, 1 plus r divided by n, and then the exponent is nt. So I'm writing it here so you don't have to keep flipping back to where you have it. So it says we have a $3,000 deposit that earns 6% annual interest compounded quarterly. So we're going to write y is equal to, p is our principal, the initial deposit, the initial amount. So that's going to be our 3,000. Then I put 1 plus, and then my rate, my R, is the 6% as a decimal. 6% as a decimal, we move it over 2 places, so it actually be 0.06. But we have to divide that by n, and n is how many times per year it's compounded. Quarterly is 4 times, so we're going to divide it by 4. Our exponent is going to be n times t. So quarterly is 4 times, and then times however many years. So it didn't tell us how many years, but if it did, that would be where we would plug it in. So that's our equation. And then we can simplify that. So if we simplify what's in the parentheses, I do 1 plus, and then I do the 0.06 divided by 4 and add that to 1. I actually end up getting that y is equal to 3,000 times 1.015, and then my exponent would be my 4t. And that's a little bit more simplified so that when I need to plug in my t, I'm able to find that out. So it didn't ask this in the original question, but I'm going to ask it. How much money would you have in your account after 5 years? So after 5 years, that means I'm plugging a 5 in for t. So I have y is equal to 3,000 times the 1.015. And if 5 is my t, then 4 times 5 is 20. So my exponent would actually become a 20. So if I plug that in to my calculator, let's see, so I do 1.015 raised to the 20th power, and then I do that times 3,000, and I get that the amount in my account would be $4,040.57. Notice I rounded it to 2 numbers after the decimal because it's talking about money. You can't have 3 numbers after the decimal if you're talking about money. So always rounding appropriately for that problem. So that would be after 5 years. Okay, so try that last one and see if you can get it set up. I haven't told you after how many years, you're just getting the equation set up. All right, so last one. So we have y is equal to my initial amount, which in this case is 5,000, and then it's 1 plus 7.2% is actually 0.072. And then it's compounded monthly, which would be divided by 12. My exponent would be 12t. So then I could simplify that one again if I wanted to 5,000. And then when I simplify what's in the parentheses, if I do 0.072 divided by 12 and then add 1 to it, it's actually 1.006 to the 12t. And then again, I could tell you how many years, and you could plug that in for t and figure out how much money you would have in your account. Okay, so that's our exponential growth and decay. Take a second to write your summary, mark anything that you have questions on, and make sure and get those questions answered tomorrow in class.